Okay, today we shall be looking at the first topic in Cambridge A-level physics, A2, motion in a circle. As you can see on the screen, I put in the important terms, what we need to know about circular motion. The first point here is motion of a circle of a body following a circular path about a fixed point at a constant speed. Now, which means that the motion in a circle simply means the motion of a particle of a body following a circular path about a fixed point with a constant velocity. The second point, I said the speed of the object is constant. For a motion in circular motion, or for an object in circular motion, the speed is always constant, but the direction changes. These are very important, but the direction changes all the times. Now, it is only in circular motion that the body can have uniform velocity and still possesses acceleration. Like I said earlier, remember I said that the speed of the object is constant, the magnitude is constant, but the direction of the object changes all time. The fact that the direction is changing, it simply means that the body is accelerating because the direction of the body is continuously changing. That's the second point. The third point, the constant changing direction means the body has velocity, which changes constantly in direction. I just mentioned that not quite long. The last point, on the important point in circular motion, acceleration is used when velocity changes. This means the fact that the velocity is changing, which means the body is accelerating. And the acceleration is always directed toward the center of the circle and perpendicular to direction of motion. This last point is very key. Remember, I said that a body undergoing circular motion does so with a constant speed, but changing direction. Once the direction is changing, which means the body is accelerating, and the fact that the body is accelerating, the acceleration is always directed toward the center of the circle and perpendicular to the direction of motion. Now, these are the simple definition of motion in a circle. Now let's see the terms we use in circular motion. Let's see the terms used. Now, let's see terms used. In circular motion. I'm going to draw a diagram to reflect the 4 points I mentioned earlier. Let's see the terms used in circular motion. Now, this is a diagram. This is a circle. Now, let's see this is a point. This is the object at point A. The direction of the object is always tangential to the circle. This is the body at point A. The body has changed the position. Remember, the direction is always tangential to the circle. This is the body at, or let me put it like this. Let me put it like this. Let me use different color. This is the body at A. This is the body at B. Now the body changed direction. Now the body is undergoing circular motion. The body is going in circular path. This is the body at C. You can see the way I'm drawing the direction of the body. The direction of the body is tangential to the circle. Now, I'm going to choose just 2 points. You can see, look at the body at point A, point B, point C, point D. It shows that the body is going a circular path. Now, and from one of my points, I said the body is always accelerating toward the center. This is the center of the circle. From here to here is radius of the circle. This is point 0. From here, I'm considering these 2 points, A and B. Now, the body has been displaced from A to B. So it has been displaced from A to B at an angle theta. Now, this is the body. Now, the first term we use in circular motion is this. The first term is, let's define the angular velocity. Let's see what is the meaning of angular velocity. The symbol for angular velocity is this. Now, angular velocity, this is defined as the rate of change of angular displacement, the rate of change of angular displacement, the rate of change of angular displacement. That's our angular velocity. Now, when you check, let me go back to the diagram. Check my diagram. Just pick any point. I'm particular about point A and B. The same thing. What is happening between point A and B? The same thing happening point C and D, and point B and C. Now, initially, body was at A. Now it's at B. It's moving in circular path. You can see the direction continuously changing. Now, from A to B, it's been displaced, and I define angular velocity as the rate of change of angular displacement. What is the angular displacement from A to B? The angular displacement is theta. So therefore, angular velocity is the rate of change of angular displacement. The angular displacement is theta over time. Rate of change. Anything rate involves time. So angular velocity is the rate of change of angular displacement. Now, where this is angular displacement, the angular displacement is measured in radian. So if the object, like I said, if the object moves from A to B so that the radius OA move through an angle theta, its angular velocity. So theta over time. So which can be written also, the angular displacement can also be WT. So the angular velocity is rate of change of angular displacement, and is measured in radian per second because time is measured in seconds. So angular displacement is measured in radian per second. Now let's see another term. Number 2, what is period? What is period? The symbol for period is capital letter T. That is the symbol for period, capital letter T. Although, we define, okay, now I'll be using the first definition of angular velocity. I'll be using it to expatiate more or elaborate more on period. Now, the general definition in ways for period is time taken to complete one oscillation or time taken to complete one cycle. But in this case, this is how we define period. Now, when the object completes or rotates in one revolution, what I mean by when A moves from A to B to C to D back to A, that's one revolution. Then that's what we call the time will now change to period. Let me put it like this. When the object rotates in one revolution, the time taken will change to period. Small t will change to period. So therefore, angular velocity, which is angular displacement over time, will change to, at that point, when t is equal to capital letter D, which means the object has rotated in one circle. At that point, when the object rotates in one circle, the angle is 2 pi radian. So angular velocity at that point will be 2 pi over period. Hence, period is equal to 2 pi over angular velocity. This is how you can understand period. When the object rotates in one revolution, at that point the angle turns to 2 pi radian and time taken turns to 1 period. So the parameter changes using this formula. Then we have this, then make t the subject of the formula. Then since period is equal to 2 pi over angular velocity, we call that period can also be what? 1 over frequency. So substitute in that equation. So 1 over frequency will be equal to 2 pi over angular velocity. Cross multiply. So angular velocity can also be 2 pi f. Angular velocity can also be 2 pi f. That's it. So from here we can also make frequencies. So the formula frequency can be W over 2 pi. This is another one. That's it. Now let's see another terms again. Let's see another terms. Let's see what is called radian. Let's see what is called radian. Let's see what is called radian. Now, let me define radian first. Radian. Now, this is defined as the angle subtended at the center of the circle. The angle subtended at the center of the circle by an arc. Equal of length. Equal of length to the radius. Equal of length to the radius of the circle. CIE usually asks to the student to define this term, radian. Let me explain it. Radian is defined as the angle subtended at the center of the circle. If you remember our first diagram, the angle subtended at the center of the circle by an arc equal of length to the radius of the circle. Now, remember the length of an arc. The formula is r theta in your circular measure in math, your P1. The length of an arc is r theta. So theta in this context is angular displacement. Theta is length of an arc, s over radius. Look at my definition. I said radian. Radian is the unit of angular displacement. If you remember what I said earlier, it's measured in radian. Angular displacement is measured in radian. So radian is the unit of angular displacement and is defined as the angle subtended at the center of the circle. Of course, you remember, it's defined as the angle subtended at the center of the circle by an arc. Look at the term, by an arc equal of length to the radius. Now, if theta is radian, that's 1 radian. So 1 radian equal to what? S over R. When you cross multiply, S equal to R. So which means by the time we are talking about 1 radian, it means that um, um, the arc, which is S, is equal of length to the radius of the circle at 1 radian. That's it. So let's move to the next one. Now, the next one is, let's see the concept. Let's see the concept of centripetal acceleration. Let's see the concept of centripetal acceleration. Let me draw the diagram again for a body undergoing or moving in a circular motion. A sketch diagram. It's a circular motion. So the body was initially here, is moving at tangential to the circle with a velocity VA. Now the body at this point has changed direction at point B with a velocity VB. This is VA. You know, the direction of motion, as in, if you remember when I was defining or giving the key point for circular motion, I said something. One of my points is that acceleration is always directed toward the center of the circle and perpendicular to the direction of motion. And perpendicular, the acceleration is always directed toward the center. So which means the acceleration is toward the center. Let me use another color. Acceleration is directed toward the center and perpendicular to the motion of the circle. I'm very sure you got it. This is the center of the circle. Center to edge is called radius. This is radius. This is radius. Now, so from here, you want to talk about the centripetal acceleration. Now, from what is on the screen now, consider an object moving at a constant speed. Like I said, in circular motion, the object is always moving with the constant speed. The magnitude of the velocity is always the same, but the direction of the object is continuously changing. Look at from A to B, from B to C. The fact that the direction is changing continuously, that is the reason we say uniquely that the body is accelerating. It's only in circular motion that a body has a constant velocity but is accelerating. Don't forget, it's only in circular motion that the body has a constant velocity but the body is accelerating. What's the reason? The reason why the body is accelerating is because the body is continuously changing direction. Now, remember that speed is a scalar quantity. It has no direction, while velocity is a vector quantity. So that's why I drew the direction tangential to the circle. Now, this is VA, this is VB. Let's look at it like this now. The velocity, since the directions are different, you can see the direction of VA and VB are different, although the magnitude are both equal to V. So I'm going to say you guys agree with me that the body is accelerating because the direction is changing. What is acceleration? Acceleration is change in velocity, rate of change in velocity. Let me call it equation 1, rate of change in velocity. Now, I'm going to draw a vector diagram to properly explain this. Now, when you check this, when you check this, you can see there is a change in displacement from VA to VB. Let me draw it properly. to change. Okay, this is VA in this direction. So there's a change in displacement. This is the angle. Change from VA to VB. So I can draw a triangle to represent the velocity. Please follow what I'm doing. Now, it's okay. Um, Now, okay, VA is going up. VA, you can see VA, this velocity A. Now the fact that, look at velocity B. Look at velocity B. So, you know, the body changing from A to B. So the initial point is A. The final point is B. Change in velocity in this context. Change in velocity should be VB minus VA, because VB is final. Which means VB is positive, VA is negative. So I'm going to reflect that analysis in my diagram. So the one going up is positive. Here should be VB, and VA is opposite of VB. So VA should be going down. This is VA. So I'll call this, this is center A, B. So change in velocity. So the change in velocity is here. The change in velocity, the body is going from A to B. It should be like this. So change in velocity is VB minus VA. That's the first vector diagram. So that's the diagram here. At the same time, the body changes direction from A to B over a short time, over a short period of time. So since the time is very short, this arc, this is the length of arc. Since the time is short, I can say I can turn the arc as a straight line to form another triangle for radius. We have radius here, we have radius here, we have center here. This place is the arc, length of arc, S. Remember, this is the angular displacement, theta. So yes, theta. So we will now treat triangle AOB. Let me call this POR. We now treat triangle AOB and triangle POR as a similar triangle. This one is for velocity, this one is for the radius. We treat it as a similar triangle. So since I'm treating a similar triangle, for similar triangle, AB over PR will be equal to VB over radius. No. I'm using alphabet for now. I'm using alphabet for now. VB over radius. AB over PR. This base over this base. One of this side, AO, over one of this side here, RO, equal to the other side of this one, BO, over the other side of this one, PO. That's how we treat similar triangle. So since we've considered them as similar triangle, because the angle is the same thing, AB over PR, AO over RO, BO over PO. That's similar triangle. So let's solve them using similar triangle. So since, let me change to black. Since AB over PR is equal to AO over AO over RO equal to BO over PO. So what's AB? Our AB is a change in velocity, while our PR is the length of arc. AO, I think, is VB. RO is radius. The radius is small r. The radius is small r. VB over R equal to VA over R. If you remember how to use your sine rule, you equate any two. You equating any two. Equating any two. So we have change in velocity over S equal to VB. Equating any two, this one must be there, and equate it to any of the two, VB over R. Now, when you cross multiply, we have R dV equal to S VB. Make S the subject of the formula. That's displacement. So that's the arc, length of arc, or that's also that's the distance. So that will be R dV over VB. So from here, no, let's make change in velocity the subject formula to be easy to derive if we want to derive. So make change in velocity your subject of formula. You're going to have SVB over the radius. Now divide both sides. Divide both sides by time. When you divide both sides by time, we have dV over T equal to SVB over R. When you divide by time, that will be 1 over time. At the end of the day, velocity over time will give us acceleration. This one gives us SVB over RT, which is the same thing as S over T multiplied by VB over R. So from here we have acceleration. S is distance, T is time. Distance over time is velocity multiplied by VB over R. Since in circular motion the velocity are the same, VB is the same thing in magnitude as VA, you can say it as V. So acceleration can be V times V over R, which gives us V squared over R. This is the formula for and the proof for centripetal acceleration. Centripetal acceleration, this is the formula and the proof for it. So since centripetal